Okay, so now we get to use all this language that I spent 3 lectures developing. We won't use all of it, but still needed all the definitions. So I want to talk about the Bochmer-Kodaira identity today and see how far I get. So you've seen a version of this for domains in C by Debraj, and you should keep that in mind and try to make a kind of map between the different steps. It's extremely helpful to understand what's going on. Okay, so the data is going to be Kähler manifold. X will be Kähler, and G will be a Kähler metric. Then we're going to have a holomorphic vector bundle, E, holomorphic vector bundle on X, and it'll have a Hermitian metric. So, and then we have various things associated to this. Last time we learned about the Chern connection and its curvature. So I'll be using those. Now what we want to do is set up an identity which will give us an a priori estimate to solve the d-bar equation. Then we're going to want to use some kind of, we're trying to turn it into a linear equation that we should try to invert, and the estimate is meant to say that the smallest eigenvalue is positive. But unfortunately, the spaces are infinite dimensional, and so you need to use continuous objects, but the rest of it is a lot like doing linear algebra. So we need the correct function spaces, and these will be Hilbert spaces, so they'll be defined as follows. So actually, let me set up a little bit of notation. So for a coordinate system Z, Z1 up to Zn, and a frame E1 up to ER, so I'm moving a family of basis vectors for the vector bundle. These are over some small open set. If we've got a differential form phi, a twisted differential form with values in E, so we're going to work on NQ forms. Then we will express this differential form as a collection of functions, so phi, alpha, j bar. So there will be dz1 wedge dzn. This is the n part, and then the q part will be dz bar j, and j is a q multi-index, and then you have the frame E alpha, and there's a summation over the j and the alpha, as usual. Yes? Yes. So in the metric G, you can apply it to, say, E alpha. Actually, I don't want that. D, I want to apply to D by dzi, D by dz. Now it sort of depends. Are you seeing this as a Riemannian metric or a Hermitian metric? So I'm going to always see it as a Hermitian metric. So there will be dz bar j. And I'll call this gij bar. Or, sorry, if I'm seeing it as a Hermitian metric, I don't put a bar there. But it doesn't matter. I always get confused anyway. They're the same object. And then you have h alpha beta bar. This will be h of E alpha E beta. If my size shrinks, just cough or something, Gautam, and then I'll expand it again. Okay. So now here's a kind of proposition slash definition. So let's let phi and c be E-valued NQ forms. Then the quantity phi c, and sometimes I'll put in brackets the metrics h and g. So this will be phi alpha I bar c beta j bar conjugate, and then here I'll put so g I1 j1 bar g dot 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 g I q, sorry, the other way around. JQ IQ bar, and then the determinant of I guess it's GIJ bar, the matrix GIJ bar. I forgot to say the usual notation in differential geometry. This metric G is a metric for the tangent bundle, or the 1-0 tangent bundle. So there's a dual metric for the cotangent bundle, and it's just obtained. In general, the dual bilinear object is just the inverse transpose. You take the transpose, that's the natural operation, and the inverse is to make the direction correct. But those are usually just denoted by raising the indices. So this is the dual metric. Okay, so the proposition says that this right-hand side is independent of the choice of frame and coordinates. Choice of coordinates and frame. Okay, so that's a practical concern how to write it, but in reality, this is just the Hermitian metric on the vector bundle lambda NQ tensor E, induced by the metric for E and the metric for X. That's just its expression, but you can also check by hands if you change frames, see how these things change, and you'll see that this quantity will remain unchanged. Correct, yeah. Okay. Oh, I forgot the. So this is a determinant of this matrix. Oh, okay. There's no. Maybe I should write it just as determinant of G star. And thank you. I forgot this the metric H. And it's supposed to be different character. Okay. Right, so this is some kind of a function. I'll leave you to check this or just believe that this is indeed the expression for the metric. And now let's... So for such phi and C, I'm going to now define the L2 inner product. Phi C will be the integral, well, 1 over n factorial q factorial. The n factorial is not so important here, but q factorial is useful. And you take this phi C and multiply by the area measure. So I'm going to stop using the subscripts. It's implicit that I'm have some metrics. So this is an L2 inner product. And if you want, you can think of these metrics as the weights. And then we're going to define the L2 space. So L2 NQ of GH is going to be, well, first we start by taking, so all the sections phi of lambda NQ X tensor E with compact support. We take those things, and then we make the Hilbert space completion with respect to this inner product. So it has the advantage that we never have to worry about what the objects in this space are. They're automatically approximable by smooth things, but then we don't really know what they are from this definition. But it's standard first course in measure theory that these are equivalence classes of functions defined almost everywhere, and there's a whole theory of integration attached to that. So it's the same thing, but for us, this is a more natural definition. Maybe I want to make a kind of remark that you see here the volume form appearing, and the volume form you get by multiplying Lebesgue measure by the determinant of G, not the determinant of G dual. So that's taking this omega G to the power n is like computing the determinant of this matrix. And so this, on the other hand, is 1 over that determinant because this is the inverse transpose. So in some sense, this term is supposed to cancel this term. So there should be an object which is already a measure constructed from the two forms, and you can define it. So you can define phi C to be phi alpha I bar, phi sub C beta J bar conjugate. Now you have, let me make a short G, J, I bar. So this means the product of G, J1, I1 bar. This thing here is just this product of these things, the multi-index metric notation. And then H alpha beta bar. And now you simply put dz1 wedge dz bar 1 square root of minus 1 over 2. And this quantity is actually a measure, it's a smooth measure that's independent of the choice of coordinates in just the same way as before. So you can just integrate these things and define the Hilbert space. It's exactly the same thing. So this thing is equal to phi C dv sub G. So a lot of time, the point is that you actually don't need a volume form if you're using NQ forms to do integration. You can just take the square of such a form and you get a measure. Okay. All right, so these are going to be our Hilbert spaces, and the next thing is the D-bar operators. D-bar operators and their formal adjoints. Okay, so there are actually going to be two different D-bar operators because there are two different ways of looking at such a phi. So one of them is thinking about it as a twisted differential form, and then we have the exterior D-bar, which we defined last time. But another one is just thinking of it as a section of this vector bundle. However, this vector bundle is not a holomorphic vector bundle. So you have to be careful when you define this D-bar operator. And as we'll see, having this metric will allow us to define a natural D-bar operator. Okay, so I'll do that one second. I'll start with the standard one. And then it's going to look a little unpleasant. So here's the proposition I'm going to prove. I don't want to do too many calculations because I think it's better to do them on your own, but I should do some, and this is one of them, unfortunately. Okay. So suppose we have some phi, which is a smooth, twisted NQ form. Then we have this operator d bar, which we gave some kind of a formula for before, but now I'm actually going to write it down in such a way that the coefficients are skew symmetric, so that I could easily compute the adjoint. So the formula is d bar of phi. Maybe I should write it up here. D bar of phi is minus 1 to the n, the sum k going from 0 to q of minus 1 to the k nabla j sub k bar phi alpha j1 bar, and then the jk bar I omit here, and then jq bar. That's it. Am I still doing okay with the size? So? Okay, all right. Okay. Well, important for me to stay consistent in these circumstances. Okay, so it's a little tricky to do these things. So let me try to convince you that this is the formula. So last time our formula was d bar of phi was minus 1 to the n. So this is the proof. And we're supposed to differentiate this phi alpha j1 bar, jk bar, and then we put dz bar j wedge dz bar capital J. The only disadvantage of working with NQ forms is you have to keep writing this. I should have just stuck it in the frame. dz bar j tensor. Yeah. So this is how we either defined or derived, depending on which definition you convinced yourself of, the expression for d bar in general. This is the one you know how to do. Sorry? Yes. JQ. Thank you. Okay, but this is, in this form, these coefficients, this is not skew symmetric with respect to the j. So we would like to make it skew symmetric, and so we have to sort of reorganize the sum. So this will be minus 1 to the n, and then the sum, k going from 0 to q, negative 1 to the k, and then what we're going to do is put d by dz bar jk of phi alpha, and now we put the indices j0 and we omit the index jk up to jq. This is a q plus 1 indices. This j has a different label depending on where you see it inside the summation. And I think that's it. So dz1 wedge, dzn wedge, dz bar. So let me, so this is j sub q. This will be dz bar j q plus 1, just to distinguish that these are different indices than the previous step. Okay, so you have to convince yourself of this, and then you're done, because for the Chern connection, the d bar, the 0, 1 part, which is acting on a 0, 1 vector, is just d bar. So that's how you get this formula. Okay. This is equal to nabla j bar k for Chern connection. Okay, good. So far, so good. Okay, so now we want to compute the formal adjoint of this. So using the Hilbert space structure, we compute the formal adjoint. So d bar. I'll call it d bar star, even though later we'll use this notation also for the Hilbert space adjoint. So remember that this is just defined by d bar star phi, say eta, is supposed to equal phi d bar eta for all eta compactly supported. PQ, NQ minus 1 forms with values in E. Okay, so what is that going to be? That's 1 over n factorial q factorial, the integral over x of phi alpha j1 bar jq bar times d bar of eta. So this will be -1 to the n, summation k going from 1 to q, -1 to the k plus 1 or -1, whichever, they're the same. Then you have nabla j bar sub k eta beta j prime 1 bar j prime this should be prime, j prime k omitted, j prime bar q. And you have the complex conjugate of this, and then you have the rest of the stuff. So g j prime j bar h alpha beta bar, and that's good enough. That's times the Lebesgue measure, dv of z. All right, so okay, so now what I want to do is to apply integration by parts to move this operator to this function. So you may wonder, how are you applying integration by parts? Because this is some kind of potentially complicated operator. So it's a complex conjugate. When it comes out of the complex conjugate, it's the 1-0 part of the connection. So what exactly is going on there? Well, you basically just say that since this is the Chern connection, it is compatible with the metric. So that means that you can just move it there with getting just a minus sign. Because so if you take this quantity and you add to it when the connection is here but without the complex conjugate, then you get the exterior derivative of some expression. That's metric compatibility. But you have these compactly supported forms, eta. So by Stokes' theorem, this is going to be the integral over the boundary of some domain that contains the support, and that's 0. So it's just exactly integration by parts. But the reason for using this connection as opposed to a derivative is that you don't have to start differentiating the metrics and keeping track of that. You know that that information is contained inside the connection. So it really simplifies the structure of the computation. So this will be negative n plus 1. You get the minus 1 from the integration by parts. Nabla jk phi prime, phi alpha j1 bar, jq bar, and then you have times the sum, k going from 1 to q, negative 1 to the k plus 1, and then you have eta j prime bar 1, jk prime bar removed, jq prime bar. And now I'm going to do a little something. So see this j prime is acting on this quantity, and this metric here has a product of a bunch of metrics. And so I'm going to take the one corresponding to k prime and put it here. So this will be j jk jk prime bar. And then the rest of the things I have here will just be j did I get that the wrong way? Sorry. jk prime j bar. j1 prime j1 bar, and jk prime jk bar omitted, jq prime jq bar, and then h alpha beta bar dv of z. Right. Okay. So now what I want is I notice that, well, I'm using some of the indices here and omitting one, but they're always the same term. But here, the index jk moves, and that's the one I'm integrating with respect to. So, in fact, I could just sort of change these indices by taking jk and moving it to the first slot. But when I do that, I have to jump over k minus 1 indices, and the sign of that will be negative 1 to the k minus 1, which is also negative 1 to the k plus 1. And so equal 1 over n factorial q factorial, and then you have the integral over x minus 1 to the n plus 1, and then g, so I j bar nabla I phi alpha j bar j1 bar j q minus 1 bar. Yes?
When you're carrying out a Stokes theorem computation.
Yes.
So presumably you need to smooth a compact.
I do more than presumably assume that I have such a form. Okay, so, and then I have, doesn't have to be. I mean, it's, you can, sort of depends what you mean by formal adjoint. For me, a formal adjoint is something that acts on smooth things and is only supposed to confirm when tested against compactly supported things. It just saves a step that when Debraj gave us the formula for d bar star, he noted, or maybe it was I noted, because it's convenient for what I want to say here, that in fact it's an actual differential operator that makes sense on smooth forms. So I like to define the formal adjoint so that a priori that's true, but it's just a definition. Okay, so K going from 1 to Q, and now I don't have the sign anymore, but now I've changed the names of the indices, so this is actually, these are all the same, independent of K. So J1 prime bar, maybe there's a beta here. Yep, I forgot my betas there. J Q minus 1 prime bar. Conjugate. And then metrics that I don't want to spend time writing again. There are those metrics, or maybe I should just write it. It says G, J, J prime, J bar, H alpha beta bar. Easy as okay, but notice, so as I said, these terms are always the same. So there's Q of them, but in every one I've changed the indices to make them the same index. So now they've all become the same. So I just have Q of these things. So actually I can get rid of this summation and just divide by Q. Okay? And that's exactly now this expression. It's the inner product for Q minus 1 forms. So then we see that, d bar star of phi is -1 to the n plus 1, g I j bar, nabla I, phi alpha, j bar, j1 bar, jq bar, dz1 wedge, dzn wedge, dz bar j, tensor e alpha. Okay? So that's the formula for the formal adjoint. So this is a very similar calculation to the one that was done for us in the one variable case, but because of getting the skew symmetry right in order to get the second computation, it looks a little messier. It's really very much the same thing. And then we have this nice machinery from complex geometry that makes a lot of formulas very clean, relatively speaking. Okay, so far so good. Okay, so we all remember these conventions. So now, what about the evil d bar, other d bar operator, the evil twin? Okay, so in this one, we view phi as a section. So in other words, a 0,0 form. So that's what I mean by section, with values in the not holomorphic vector bundle n lambda qx tensor E. This is not holomorphic vector bundle, but it's almost a holomorphic vector bundle. The only problem is the Q, right? So if we write out what this was, this is the nth, or the determinant of T10 star of x. That's nice and holomorphic. And then it's the qth tensor power of this vector bundle, so T01 star of x. And that's the vector bundle that's not holomorphic. This E is holomorphic. So this is our our bad citizen. So we have to make this citizen conform to our very oppressive geometric community. So how do we do that? In fact, because we have a metric G, so the metric G induces an isomorphism T 0, 1 star X. Let me call this thing F with T1, 0 of X. No star now. Okay? So how do you write down this isomorphism? Well, so if we have some alpha, so it's a 0, 1 form, then it maps to this form F alpha. And what does F alpha is now supposed to be a 1, 0 vector field. So that's defined by so G of this F alpha acting on a 1, 0 vector C. As this is a Hermitian metric. Remember, I think it was metric for T1, 0. This is, by definition, alpha contracted by the vector bar, the 0, 1 vector. Okay? This is the usual way that you turn differential forms into vector fields. So for students in calculus, they first see this for the derivative. So they just get the gradient, and the first time you learn differential geometry, you learn that the gradient is not a good thing. It depends on a choice. It's the differential that matters. So this is the correspondence in this setting. Okay, so right. So if you have such an isomorphism, then you can map this thing by an isomorphism induced by this F, which I'll also call F, to lambda n of T, let me say lambda n 0x tensor lambda q of T1 0x tensor E. And this is a holomorphic vector bundle. And so therefore, any section of this you can apply d bar to, because we know how to apply d bar to holomorphic vector bundles. And so we're going to define the sort of mirror d bar operator, nabla bar, to be, so first you apply f, then you apply d bar, and then you go back with f inverse. But remember, you've raised the degree of the form, so these, strictly speaking, are different f's. One of them is for q, and the other one's for q plus 1. But there's a standard way of applying it. Okay, so, and now you can compute the formula for this guy. It's actually much simpler, and so because of that, I'm not going to go through the computations. I'll just tell you what it is. So let me say proposition. Right, so maybe I'll sort of go through the proposition. So nabla bar of phi, well, you want to first of all turn this phi into a multi-vector field with values in the correct vector bundle. And so you do that by raising with the metric. So that will be, say, g I j bar phi alpha j bar, and then you apply d bar to this thing, and then you lower again, say g I l bar. So these are the isomorphisms f. Maybe I should have used g. But because this is the Chern connection, it's actually, so anyway, and then you have all the frame stuff, which I don't want to write, but because it's the Chern connection, this actually just turns out to be a d bar of phi alpha j bar. So that really looks a lot like the d bar operator, which is a little frustrating the first time you see it, because you wonder, did you need to say all this nonsense? Nabla bar, yes, thank you. Did I need to discuss this whole F? But the actual difference comes in the frame. So then you have this differential form tensor with dz1 wedge dzn wedge dz bar j tensor e alpha. So what I mean here is that this quantity here is not a wedge product, but it's d phi alpha j bar, dz bar, say k, and then dz bar k tensor this whole business. So it's not a differential form, it's actually a kind of a tensor. You should think of it this as the coefficient here as something like phi alpha j bar and k bar. It's not a multi-index anymore, but it's a multi-index together with a single index. And so there's actually, these live in a different Hilbert space than the other things do. So you actually have to define the correct Hilbert space to get the formal adjoint. Let's see, so I guess this will be T star 0, 1 x tensor lambda n q x tensor E. See, so that's the difference from the other ones. These are not q plus 1 forms. They're 1 forms with values in the vector bundle of differential forms. Okay, so, but it's obvious what to do because you have a metric for this thing, and it also induces a metric for these, and we already have a metric for this one as well. So you just design the Hilbert space in the correct way. So I'm not going to go through writing it down. It's written in the notes if you want to do that. But so there's some other inner product, and then you're going to define the formal adjoint, nabla bar star phi. So this eta will again have compact support. And this should be, by definition, equal to phi. So if you want to, just for a moment, to say here the index Q1, so 0, 1, 10, NQ forms, then this one will really be, sorry, this is just the standard Hilbert space we had before, and this one will be the Q1 Hilbert space. This is Q1 for this thing. But anyway, this is just how you have to do it. Okay, so, and then this formula is also very easy to compute. So the formula is, looks very similar, but it's slightly different. So it's negative G K J bar nabla K, this is the Chern connection again, in the d by dzk direction. And then you have phi alpha J bar, J bar, J bar, EZ1 wedge EZN wedge EZ bar J tensor E alpha. So, okay, for whatever it's worth, those are the two formulas for the other D bar operator and its formal adjoint. Okay, so now I'm finally ready to write down the Bochmer-Kodaira identity. I'm going to write it as a theorem, and then I'll explain. So it'll be again in kind of metaphoric notation. So we have our X with the Kähler metric G, and then we have this E with the Hermitian metric holomorphic vector bundle. So this is holomorphic Hermitian. And so now we're going to define, it's a standard notation for the Laplace-Beltrami operator associated to D bar. So that'll be D bar star plus D bar star D bar. This acts on NQ forms with values in E and produces an NQ form with values in E. This is the definition. And so then the statement is that this box operator is the other Laplacian plus some 0th order term, which I'm going to write in this way, and I'll tell you what this is right now. So this is supposed to be how the curvature acts on E-valued NQ forms to produce E-valued NQ forms. Because remember that the curvature is itself a matrix of two forms. So you can't just take a wedge product, you'll be in the wrong degree. You have to somehow take a contraction, but the contraction's a little complicated. Here's the formula. And it'll pop out of the derivation. So this is, so remember the curvature, I'll write it as theta of H, but it's a, it's a matrix of 1-1 forms, JK bar. And then I'm going to put here phi beta J1 bar. And then in the kth slot, I'm going to put an index L bar, JQ bar. And then I'm going to contract I and L bar. I'm going to sum L from 1 to Q. So you see, you're acting on every index separately. And this is, it may look a little scary the first time you see it, but it actually makes sense because it's the curvature acting on some product bundle. The lambda Q is a qth wedge product of T01 star. And so, according to our philosophy, when you have products, the connections act by summation. They act on each factor separately. It's the product rule for differentiation. So that's why this appears there. Anyway, that's the formula. So okay, so essentially, the way you prove it is you just take the formulas that we had for these things and you compute this box. You will see that one of the terms that appears is this one, and then the rest of the terms look something like this. So they will look like, and this takes some work, but I don't think it's worth doing on the blackboard. It would be GIL bar, nabla I, nabla JK bar, phi alpha, J1 bar, LK bar, AQ bar. So this is the remaining term. When you write this down and collect the terms carefully, you're going to have a term that looks like this, and then the remaining part will look like this. But you have to do some work to see that. But I provided all the calculations, surely with some typos. So that's a challenge, you know. If you don't understand it, you're probably not wrong. What's the point of this? So at the very beginning, let me write this formula away from all the clutter. Better to write it this way. So now what you've got is two possible Laplacians that you get from d-bar operators on NQ forms with values in E. And their difference is this curvature. And if you look at the way the derivation is done, you can see why it's curvature. The reason is that whenever you compute these adjoints, you're doing integration by parts. And when you combine these exterior operators, you have to often interchange the direction of differentiation. And so when you have a curved space, one of the ways of seeing that is that if you want to differentiate in this direction and then in this one, so you do this, you take some short paths, you follow one and then you follow the other. Or you do it the other way around, you follow one, then you follow the other. So the only time that will always be a closed figure is when the space is flat. And so it comes up as curvature here because you're really interchanging derivatives. And so it makes sense geometrically as well, although I've not yet found a way to just argue by pure geometry with no calculation that this formula should hold. It also uses heavily the Kähler structure. So we used it at several places. First of all, that it's the Chern connection, but also that it's the Levi-Civita connection, so that it annihilates this metric, and is symmetric, and so on. If you didn't use this, if you didn't have a Kähler metric, then you would get some other terms, and there would be something called the torsion that would appear in there, and that complicates things significantly. Plus, it's not clear to me what kind of, the theorems you would get should not be very canonical, because you know, in the pseudo-convexity condition, the Kähler feature plays a crucial role, at least near the boundary of the domain. So I think it's a fundamental thing, but you could get theorems if you just crank up the curvature high enough, but I don't know that you could state it in such a clean way. Okay, so why is this formula useful? Well, the nice thing about Laplace operators is that they're always non-negative operators. So if you apply the Laplacian to phi and take an inner product with phi, right, this is how you measure the positive definiteness of this linear operator. Well, if you look at its formula, this is going to be d phi squared plus d bar phi squared plus d bar star phi squared. And that's, of course, non-negative. And nabla bar star nabla bar phi is norm of nabla bar phi squared. By the way, there's no nabla bar star because this is a zeroth order. It's a section. It's a 0-0 form. And so the adjoint always acts on the lowest degree by 0. So it's still a Laplace-Beltrami operator. Just there's no other term because you're seeing it as a lowest order section. Anyway, so what you're saying is that you have these two non-negative operators, and non-negative is not enough to invert it, but if you happen to know that the curvature is a positive operator, then you actually have a lower bound for the eigenvalue of for the eigenvalues of this box, if you know that this curvature is positive. So that's the hypothesis in Hörmander's theorem, exactly to make this Laplacian invertible. I think there's just a few more minutes. So let me show you another way of trying to. This will be sort of a preliminary to what I'm going to do next lecture. So suppose we want to solve the equation box V equals phi for some phi. Okay? So V is for the unknown and phi is for given. So, how do we get this? Okay, so let's define a Hilbert space. So we're going to assuming that this operator, it's some kind of operator on differential forms that will say that it's bigger than or equal to some positive constant times the identity transformation. This was the hypothesis in Hörmander's theorem, but I'm actually going to do this for the Laplace operator. So let's make a Hilbert space. So this is going to be, we're going to take the set of smooth forms, I don't know, say eta, such that, so d bar eta squared plus d bar star eta squared is finite. And this eta should be smooth. And let's assume, for now, we're going to deal with this later, so let's assume that X is compact. There is no boundary to deal with. So we just can take smooth forms. We don't have to say compactly supported. So this is some inner product space, and then we'll take the closure with respect to the associated norm, right, which is just the inner product d bar eta d bar zeta plus d bar star eta d bar star zeta. No, not here. So I have this H. You'll see why in just a minute. And so what does this hypothesis mean in terms of this norm? This hypothesis exactly means that d bar star eta squared plus d bar eta squared is greater than or equal to c times the norm of eta squared. So this hypothesis implies that this is a well-defined inner product. Okay? And so now you have this structure. It also says that the inclusion of this space into the L2 space is bounded because of this constant c. But I'm not going to use that. So, okay, so now let's let's take this this phi that we're trying to solve the equation for. So we want to solve this box V equals phi. So let's send eta to the inner product of eta with this phi. Okay. So I claim that this is a bounded linear functional on H. So the way to see that is that if you compute the norm of this thing, say the square norm of the image, that's less than or equal to 1 over c times the norm of phi squared, and then times c times the norm of eta squared, just a big constant, small constant, Cauchy-Schwarz. But the c times the norm of eta squared is bounded by this. Okay, so that shows you that actually this thing is a bounded linear functional on H itself. Right? So by the Riesz representation theorem, there's some V which represents it. And so what you get is that this V satisfies d bar eta d bar V plus d bar star eta d bar star V equals eta phi. And so this is what it means to be a weak solution of this equation. And now there's a kind of punchline which I will say in vague terms and maybe give it in the problem session to resolve this appropriately. I claim that if this phi is d bar closed, then V is also d bar closed. So that's going to be the exercise. It's a little bit trickier to prove than I'm going to do now, but I'm going to just assume that this V is smooth, which happens to be true, but that's much harder to prove. So if this V is smooth, then what you're getting is exactly box V equals phi. So we write this as d bar star V plus d bar star d bar V. That's equal to phi. Right? This is the same equation. And now I can apply d bar to everything if this smoothness really holds. Right. Right. Okay, but this term has d bar squared, so that's 0. And this is closed by hypothesis, so that's 0. So that means that d bar star, d bar V is 0. So d bar star, d bar V is equal to 0. So you can pair that, for instance, with d bar V. Take L2 inner product, and that's still 0. But this is just equal to the norm of d bar star, d bar V squared. Right? And so that's 0. So that means that the box of V is equal to d bar star V only. So if you take this to be U, then this is a solution of this equation. And I claim that it also has the L2 estimate. In fact, it's completely trivial because the norm of U squared is just the norm of V squared with respect to H, because the second term here, the d bar star of d bar of V is 0, right? The first term is 0. But by the Riesz representation theorem, you not only get a solution, but the solution has the same norm as this linear functional, so it's bounded by this same constant. Okay, so it's kind of interesting that, sorry? It's d bar star Z. So this solution has one additional interesting feature, which is that it is orthogonal to the holomorphic function, to the d bar closed forms. If you take d bar star V and take inner product with the d bar closed form theta, you do integration by parts, and you get, so you move this to here, it's d bar closed, so you get 0. So it's actually the smallest possible solution. Any two solutions differ by something that's d bar closed, and so if you're orthogonal to the d bar closed thing, that's the minimal norm. So you actually produce the optimal solution here, but the estimate is no better than the one produced by Hörmander's theorem, which is not necessarily producing the minimal solution. Okay, sorry for going a little over time. I wanted to show you that you don't, if you want to have very soft theorems in certain special cases, you actually don't even need to talk about density of smooth forms in the domain of the operator. Okay.